Hello everyone, welcome to this lecture in the Build Large Language Models from Scratch series. This is the second part of the multi-head attention lectures. In the previous part, we looked at implementing multi-head attention in the following way. What we did is that we had the input tokens. So let me show you this figure which summarizes everything. Yeah. So this was the input matrix which we had. Essentially, the number of rows here represent the number of tokens which we have, and each token was encoded as a three-dimensional input embedding vector. Right? In the first part of the multi-head attention, what we essentially did was we created multiple weight matrices for the query, key, and the value. So if we have two attention heads, we'll create two weight matrices for the query, two weight matrices for the keys, and two weight matrices for the values. And then we will multiply the inputs with these weight matrices to get two queries, two keys, and two values. So the main problem with this approach is that here you can see that there are two matrix multiplications which are needed. As we saw earlier, GPT-3 used 96 attention heads. So if you have 96 attention heads, you will need 96 multiplications to get the queries matrix, 96 multiplications to get the keys matrix, and 96 multiplications to get the values matrix. That's not very efficient, right? So today what we are going to see is that how can we make sure that the number of multiplications are reduced. In particular, what if we just need to do one multiplication for keys, one multiplication for queries, and one multiplication for values. And then once we do one multiplication, then we can split the queries again into two parts. We can split the keys into two parts, and we can split the values also into two parts for two heads, and then we can perform the rest. So once we get the copies or the multiple matrices for queries, keys, and values, what we can do is multiply queries with keys transpose to get the attention scores. Then we can get the attention weights, and we can multiply them with the values to get the context vectors. So the rest of the procedure can be a bit similar, but what if we can reduce the number of matrix multiplications at the start? This is what we are going to look at in today's lecture. So let's get started. This procedure is called implementing multi-head attention with weight splits, and it's definitely much more efficient than the multi-head attention which we saw previously. So in the previous lecture, the way we implemented multi-head attention was something like this. We had the causal attention module, and we calculated the causal attention module result, which is the context vector for every single attention head. And then we concatenated the results from the different uh, context vectors together, and that led to a large matrix. This was the process. Now what we are going to do is we are going to follow a slightly different procedure, and that's called multi-head attention with weight splits, and it's much more computationally efficient. So the main idea is that in the previous code we had maintained two separate classes. We had maintained a class for the multi-head attention wrapper, and we had maintained a class for the causal attention, and then we combine both of them into a single multi-head attention class. So here in the top, what you can see over here is what we did previously. We performed two matrix multiplications to obtain the two query matrices q1 and q2. What we are going to do right now is, what if the weight matrix which we start out initially itself was a larger weight matrix, and then we multiply the inputs x with the query matrix to get the queries, and then after that we split the queries into two components. So here you see the difference. In the previous case we multiplied x with wq1 and we multiplied x with wq2, but what if we multiply x with a wq, which is already a large matrix which consists of d out. So here you see the dimensions of this initial weight matrix are larger, and that these dimensions already include the number of heads. So this dimension 4 is the d out, which is 2 multiplied by the number of heads. So this d out is already specified before. So the weight matrix for the queries, keys, and the values which we specify already will kind of include the head dimension. And then when we get the queries, keys, and values, we will split them based on the number of heads. So here we can see we split the queries matrix into two, q1 and q2, because there are two heads. So ultimately the rest of the procedure will remain the same, but we are just reducing the number of matrix multiplications. So if you look at this weight matrix right now, the number of attention head is specified, right? uh, so how is it specified? So d out is equal to 4, and d out is equal to head dimension multiplied by the number of heads. So the head dimension is equal to 2, because each head has a dimension of 2. This is what we had done here. Each head had a dimension of 2. Each attention head, here is, you see, d out equal to 2, which was implemented in the previous case. So each head had a dimension of 2, and there are two heads. So the d out in this larger trainable q matrix already includes number of heads. I'll explain to you in detail what this means. Right now, if you just get an intuitive idea of what we are trying to do, that will be very helpful. Okay, so now let us get started with the code. So we are going to implement multi-head attention with weight splits, right? So instead of maintaining two separate classes, so here you can see earlier in our code, we had a causal attention class which did all the computations of attention scores, attention weights, etc. And then we integrated this causal attention class with the multi-head attention wrapper. So we had a multi-head attention wrapper, and we created multiple instances or multiple causal attention objects within this wrapper. Now the idea is, instead of maintaining two separate classes, why don't we combine both of these concepts into a single multi-head attention class? Also, in addition to just merging the multi-head attention wrapper with the causal attention code, let's make some other modifications to implement multi-head attention more effectively. So as I told you earlier, in the multi-head attention wrapper which we had earlier, multiple heads are implemented by creating causal attention objects, and the causal attention class independently performed the attention mechanism earlier, and then the results from each attention head were effectively concatenated. Now we are going to implement a class which is called as multi-head attention class, and we are going to integrate the multi-head functionality as well as the causal attention functionality, everything within a single class. The way we are going to do this is that the this class splits the input into multiple heads by reshaping the query key and value tensors. Let's see what this means. Don't worry about this sentence. In this lecture, I have constructed a hands-on example so that you understand the code which we are about to write. So first, let's look at the multi-head attention class and how we are going to define it. This code right here, which I'm showing on the screen, is at the heart of the transformer mechanism. So you see, we have the init constructor which is invoked by default, and then there is the forward method. At the end of the forward method, all we are going to do is calculate the context vector for each of the input embedding vectors. But what happens in the middle, that is the main key which you really need to understand. Okay, so I could have just taken you through this code, but I have seen that if I take students through this code, it becomes very difficult for them to wrap their heads around what exactly is going on. Especially because if you see the dimensions, there are four-dimensional tensors which are involved in this code, and there is a very good reason for why we need four-dimensional tensors. So if you just go through the code, you will think that you have understood it, but you would not have, because there are a lot of subtleties with respect to the dimensions. So what we are going to do is that we are going to go to the whiteboard, and I've constructed this example completely from scratch. So we are going to take a simple example. We are directly going to start from the input, and we are going to do all the steps on the whiteboard which are implemented in this code. Then you will find that understanding the code is extremely easy. At every step of the code, I'm going to take you to the whiteboard, and I'm going to explain to you what exactly is going on. Okay, so let's get started. I've tried to distill this down to 11 steps, and I will explain everything related to matrices, dimensions extremely clearly. I will not assume anything. Everything is written down on the whiteboard so that you will not be afraid of this code. I have seen several other YouTube videos and even lectures where uh, people just explain this as if it's very easy to understand, but you need to decompose it into individual layers and explain every single one of them. Okay, so I'm going to start with the forward method, and I will explain every single line here step by step. So first, the forward method takes the input x, right? Let's see what that input looks like and what it means. So the first step to the the multi-head attention with weight splits, that code or the multi-head attention class, is that we have to start with the input. The way we will specify the input is that the input has three dimensions. The first dimension is the batch, the second is the number of tokens, and the third is the input dimension, right? What is this d in? The d in is basically every token is represented by a vector embedding. So this d in is the dimension of that vector embedding. So 1 comma 3 comma 6 means that I have three tokens. You can think of one token as one word for simplicity. So let's say the three tokens are the cat sleeps. Let's say these are my three words. Then what we are essentially doing here is that we are converting each of these words into six dimensional vectors. So the will be a six dimensional vector, which is the first row. So which is the first row over here. So look at the first row over here. This is the six dimensional vector for the, this is the six dimensional vector for cat, and this is the six dimensional vector for sleep. So you will see that this is a 1 by 3 by 6. For simplicity, I have taken the batch size equal to 1. Okay. So this is a 1 by 3 by 6 tensor. Why 3 by 6? Because we have 3 rows here and we have 6 columns. Each row consists of six dimensional vectors. So I hope you have understood how the input has been defined. So here you can see the input shape is b comma number of tokens comma input dimensions. So I hope you have understood this. Okay. Now let's come to the next step. The next step is what we have to do is we have to essentially decide two things. We have to decide what our output dimension is going to be, and we have to determine the number of heads. This output dimension is basically, we have the input embedding vector for each token, right? Ultimately we will get a context vector for every token. So ultimately, similar to this input embedding matrix, which is 3 by 6, we will have a context embedding vector which is 3, because we have three tokens, multiplied by d out. So now we have to also decide what is d out, which is the so each token will have a context vector. What is the dimension of that vector, we have to decide. So now I am deciding that d out will be equal to 6, which is same as d in. This is typically done in GPT based models. The d in and the d out are the same. Second thing we also have to decide is how many attention heads do we want to have. So I have decided that we are having two attention heads right now. In GPT, the number of attention heads are 96 and the D out is also pretty large. But exactly what we are doing right now can be scaled to a larger D out and larger number of heads. Okay. So I'm using D out is equal to 6 and number of heads equal to 3. So then each head will have a dimension which is called as head dim, and we'll look at that also later. Each head will have a dimension of head dim, which is equal to head dim, which is equal to essentially the d out divided by the number of heads, which is equal to 6 divided by 2, and that will be equal to 3. So then the dimension of each head is equal to 3. And since there are two heads, the total D out will be equal to 6. Okay. So this is the second decision point. The third decision point which I have to make is that I have to initialize, or it's not a decision point rather, but it's the third step. So the third step which we have to do is initialize trainable weight matrices for the key, query, and the value. So we have to initialize WK, WQ, and WV. Okay. So remember that the input which we have, which for now can be thought to be 6 rows and 3 columns, has to be multiplied, 3 rows and 6 columns. So the input is 3 rows and 6 columns. So when you construct these trainable weight matrices for the keys, query, and value, their first dimension has to be equal to d in, because if you look at the input dimension, the number of the last dimension of the input is d in, and for this input to be compatible with this WK, WQ, and WV in multiplication, you need the first argument here to be equal to d in. So actually the dimensions of the trainable key, query, and value matrices are d in multiplied by d out, which is 6 by 6, because d in is equal to 6 and d out is equal to 6. So we have to initialize these three matrices rather, and I have shown these random initializations here. So you can see that WQ is a 6 dimension or a 6 by 6 tensor, wk is a 6 by 6 tensor, and wv is a 6 by 6 tensor. Let me show you in code where these matrices are actually initialized. So if you look at the code, these matrices are actually initialized in the init constructor. So w query, w key, and w value, these are trainable weight matrices. As you can see, the dimensions are d in comma d out, and we are using the linear layer of neural networks with the bias equal to 0 to set the initial values for these. Why do we use a neural network linear layer? Because it's optimized for initializing the weights, so it's much better when we do the back propagation later. So this is where the trainable weight matrices for query, key, and value are initialized in the init constructor. So it's called by default when we create or it's these matrices are created by default when we create an instance of the multi-head attention class. All right, so up till now we have essentially initialized these trainable weight matrices wk, wq, and wv. Now we move to step number 4. Step number 4 is the step from which computations actually start. So we have the input now, right? And we have these matrices. We have trainable keys, the trainable queries, and the trainable values. What we'll now be doing is that we will multiply the input with these matrices to ultimately get the keys, the queries, and the values. So what are the dimensions of the input? The dimensions of the input are 1 we just write this again. The dimensions of the input are 1 multiplied by 3, because we have 3 rows, multiplied by 6 columns, correct? And the dimensions of each of these key, query, and value trainable weight matrices are 6, which is d in, multiplied by 6, which is d out. So when you multiply the input with these weight matrices, the result which you will get is 1 by 3 by 6. So you will get the keys matrix, which is 1 by 3 by 6. You will get the queries matrix, which is 1 by 3 by 6, and you will also get the values matrix here, which is 1 by 3 by 6. Let's try to understand what this 1, 3, and 6 is. So as I've written over here, 1 is the batch size, which we are taken to be 1. 3 is the number of tokens, because we have 3 tokens, and d out is basically the output dimension. So the way to interpret these keys, queries, and value matrix is that each row basically corresponds to one token. So the first row corresponds to the first token, the second row corresponds to the second token, and the third row corresponds to the third token. And there are 6 dimensions in each row, because each token is a 6 dimensional representation, because d out is equal to 6. Now let me show you in the code where this is calculated. So if you go down below, here you see the keys, queries, and values. What we have done is that we have passed in the input to this neural network linear layer. So what this does is that the trainable weight matrices for the key, query, and value are applied on this input, and we get the keys, queries, and the value matrix. As we saw on the whiteboard, the shape of this is B, which is the batch size. The number of rows is equal to the number of tokens, and the number of columns is equal to the D out, which is equal to 6. Okay, now we move to the next step, and this is the step where 4-dimensional tensors start to come into the picture, right? So until now we have 3-dimensional tensors for the keys, queries, and values, right? Why the fourth dimension needs to come into the picture is that until now these 3 dimensions are for batch size, number of tokens, and d out, but there is no dimension for the number of heads, uh, or the head dimension rather. So this is where we come to next. So what we are now going to do is that we are going to unroll the last dimension of the keys, queries, and values to include the number of heads and the head dimension. What this means is that if you look at this last dimension of the keys here, in fact even for queries and values, this is d out, right? And d out is essentially number of heads into head dimension, as we have seen earlier. So let me take you yeah, so here remember what we saw. Head dimension is equal to d out divided by number of heads. So d out is equal to head dimension multiplied by the number of heads. So that's what we are actually going to do. We are going to unroll the last dimension of the keys, queries, and values to include number of heads and head dimension, right? So we have d out which is equal to 6, which is a decision which we have made, and we have also made a decision with respect to the number of attention heads which is equal to 2. So based on these two decision points, the head dimension is fixed, and the head dimension will be equal to 6 divided by 2, which is equal to 3. So what we are going to do next is that we had this 1 by 3 by 6 matrices, right, for the keys, query and value. Now we are going to roll them into 1 by 3 by 2 by 3. So now instead of d out, we will have number of heads which is equal to 2 and head dimension which is equal to 3. So let's see what the reshaped keys, queries, and values matrix actually look like. So when you reshape the keys, queries, and value matrix, they start looking like this. And I'll tell you how to interpret four-dimensional tensors also. So for the sake of simplicity, let's first analyze the queries matrix. So this matrix is 1 by 3 by 2 by 3. How do you analyze this four-dimensional tensor? For now, forget about the first, which is the number of batches. Okay. So next look at 3. So this 3 is the number of rows. So this is my first row, and this is my first token also, right? This is my second token, and this is my third token, correct? That's why there is this 3. Now let's look at this 2. What is this 2? This 2 is the number of heads. So if I go in each token right now, let's say if I go in the first token, the first row corresponds to the first head and the second row corresponds to the second head. That's why there is this 2. And if I go within each head, I'll see that there are three dimensions: the first dimension, the second dimension, and the third dimension. So remember, the head dimension is equal to 3. So the way to interpret this matrix is start from the outermost value. So 3. Why 3? Because there are 3 tokens. Then go to each token. Why 2? Because there are 2 heads in each token. Then go within each head. Why 3? Because the dimension of each head is 3. Each head is a 3-dimensional vector. So in this same way, we can analyze the queries, the keys, and the value matrix also. So the keys matrix will also be 1 by 3 by 2 by 3, and the values matrix will also be 1 by 3 by 2 by 3. As I mentioned before, let me repeat it again. Each row over here is a token. So if you look at the value matrix, let's look at the second row. The second row corresponds to the second token. If you now look at the first row of the second row, this, that is the three-dimensional head vector for the first head. If you look at the second row, that's the three-dimensional head vector for the second head. Remember, every token has two attention heads, so you can think of as two people paying attention to each token, because we have two attention heads. That's why there are two rows corresponding to every token. Now if we come to the code, this line has been mentioned over here. So see, we have to unroll the last dimension. So now the d out will be replaced with the number of heads and head dimension. So this is exactly what has been done over here. Keys dot view. So now keys will be replaced with keys dot view b common number of tokens, common number of heads, and head dimension. This is exactly what we just saw on the whiteboard. So in this step, the three-dimensional tensors have been converted into four-dimensional tensors to include the number of heads and the head dimension. Great. Now we move to the next step. So if you see this, let's look at this argument, which is 3. Um so the shape of this is 1 comma 3 comma 2 comma 3, right? Now let's look at this first, this entry. This is 3. Now this 3 is the number of tokens, which means that currently these matrices are grouped according to number of tokens, right? So I'm saying that this is the first token, this is the second token, and this is the third token. And then I further dive into number of heads and the dimensions in each head. But it turns out that later, when we want to compute the attention scores, the only way the computation can proceed ahead is if we group by the number of heads. So instead of grouping by the number of tokens, I actually want to group by the number of heads. And we have two heads here, right? So I want to flip these dimensions. I want to flip these dimensions here, so that the first row represents the first head, the second will represent the second head, and each will have a 3 by 3. Let me show you what I mean. So now what we are going to do is we are going to group the matrices by the number of heads. Okay. So currently the keys, queries, and the values matrix have the dimensions of 1, which is the batch, 3 which is the number of tokens, 2 which is the number of heads, and 3 which is the head dimension. So we are grouping with respect to the number of tokens. But now I want to group with respect to number of heads. So again I want to switch the dimensions to be, I want to switch this to let me write it again. Yeah, I want to switch this 2 with 3, and this 3 should come over here. So I want the matrices to have the dimensions of b comma number of heads comma number of tokens and head dimension. So I want the dimensions to be 1 comma 2 comma 3 comma 3. So what I'm going to do in the code also, you'll see we are going to transpose keys, queries and value, and we are going to transpose 1 comma 2. Now why do we do 1 comma 2 over here? Because Python has zero indexing. So index 0 is this. Since we want to interchange the number of tokens and the number of heads, the indexes which we need to transpose are index number 1 and index number 2. That's why we are doing keys, queries and value and transpose 1 comma 2. So let's see what the result actually looks like. So when you make the 1 comma 3 comma 2 comma 3 to 1 comma 2 comma 3 comma 3, now the transposed queries, keys and values start looking like this. And now you will see that they are grouped by head. So the first thing what we can do is that let's look at this block in the queries. So we are analyzing the queries matrix now. The shape of the queries matrix is 1 comma, let me write it here again, 1 comma 2 comma 3 comma 3, right? That is the essentially the shape of the queries matrix, and we are going to analyze this. So let's start with this 2, which is the number of heads. So if you look at the first block here, let me erase this right now and then draw it again. Yeah. So if you look at the first block over here, which I'm marking with these curly braces, that's the first head. If you look at the second block here, that's the second head. So see now this two, because this two comes over here, now we can group with respect to number of heads. So the first block shows everything with respect to head one. And the first row over here is the first token, the second row over here is the second token, and the third row over here is the third token. Similarly, if you look at head number 2, the first row is the first token, the second row is the second token, and the third row is the third token. So now we have the dimensions as number of tokens, and head dimensions come last. So each token, if you see, each token has a three-dimensional vector because the head dimension is equal to 3. So the reason this helps is because since we can now group with respect to heads, we can compute the attention score for each head separately. So remember, there is one attention score. There is an attention score matrix for the head one, and there is an attention score matrix for the head two, and then we are going to concatenate them together, right? So it makes sense to group with respect to the head, and that's why this step exists. This keys dot transpose. It's very difficult for students to understand this unless you see this visual example of why we are essentially doing this transpose. The main reason we do this transpose is that here you see we are grouping with respect to uh, number of tokens here, but that's not good if you want to compute the attention scores for each head parallelly. So we group with respect to number of heads. So that's why it's important to flip number of tokens and number of head dimension, and that's exactly what we have done. Okay, now let's go to the next step. The next step is to find the attention scores. So remember, now we have the queries matrix, we have the keys matrix, and we have the values matrix in exactly the shape which we want. So now we can go ahead and find the key queries and the keys transpose to get the attention score. So let me show you how this is done. First, let me rub all of this. Okay. Okay, so now I have rubbed all of this. So what we are now essentially going to do is that um, this is the head number one, right? This is the head number one of the queries, and this is the head number one of the keys. So what this shape will help us do is that when we do queries multiplied by keys transpose, it will directly take the equivalent product of head one of the queries with head one of the keys, and then head two of the queries and head two of the keys. But remember, when we take the keys transpose, what's really important to us is that now the shape of the keys is b comma number of heads comma number of tokens and head dimension. So what it's really important to us is number of tokens and head dimension. So remember the formula for calculating the attention score is queries multiplied by keys transpose, right? So here also we are going to do queries with respect to keys transpose, but what exactly do we have to transpose? Uh, we have to transpose this. So we have to transpose the last two dimensions, and let me show you what that transposed key matrix looks like. Yeah, so this is the transposed key matrix now. Here you can see the key matrix. uh, if you see the first row, it's 0.4143 point minus 1.4023 and minus 2.7131, right? So when we do keys transpose 2 comma 3, it will transpose along the last two dimensions. So now that row which we saw has now become a column over here. So this is the keys transpose, and here is the queries matrix, and I've shown the keys transpose over here. So the queries matrix dimensions is 1 comma 2 comma 3 comma 3. The keys transpose dimension is 1 comma 2 comma 3 comma 3. So they are compatible for multiplication, and the way the multiplication will now proceed is that the head 1 will only be multiplied by the head 1 of the keys transpose. The head 2 here will only be multiplied with the head 2 of the keys transpose. And ultimately, when we do this multiplication, we will get the attention scores matrix. So this is the attention score matrix which we have. And the dimensions of this are B, number of heads, number of tokens, and number of tokens. Let me show you why. Uh, Okay, so if you look at what we are multiplying here, the queries dimensions are b comma number of heads comma number of tokens comma head dimension, right? And when we do keys transpose 2 comma 3, the dimensions here are b number of heads head dimensions comma number of tokens. So essentially you can think about it like we are multiplying two matrices with the dimensions number of tokens comma head dimension multiplied by head dimension number of tokens. So what will the resultant matrix will have number of tokens rows and number of tokens columns. And the first two dimensions here will stay the same because they are the same in both of these matrices we are multiplying. So the resultant attention scores will have the dimensions of B, number of heads, number of tokens, and number of tokens. It's fine if you forget these dimensions, but you should be able to interpret what is going on here. So let's see what is going on here. Remember, we are grouping with respect to head, so that stays the same. This first block which I've highlighted right now, that is head number 1, and this second block which I've highlighted right now, that is essentially head number 2. This is the first thing to understand. Okay, then what we are doing, when you look at the, let's look at head number 1 for now. If you look at the first row, the first row essentially consists of the attention score between of the first word with all the other words, right? So remember our sentence was the, actually let me write it over here, that will be much better. So our sentence was the cat, the cat, and here it was sleeps, right? The cat, let me just write it over here. Yeah, the cat sleeps, and these same words I am also going to write over here. So the first row is, let me write it over here. Actually, the first row is the second row is cat, and the third row is sleeps. So that's why the final two dimensions are number of tokens comma number of tokens, because if you look at the second row now, if you look at the second row now, the first element of the second row tells us information about the attention between cat and the second element of the second row tells us the information between cat and cat. So if the query is cat, how much attention should you pay to cat? The third element here tells us the information between cat and sleep, which means if the query is cat, how much attention should you pay to sleep? So that's why the shape of the attention matrix for every head is number of token rows and the number of token columns, because an attention score exists between each token for every other token. So whenever you see these dimensions, right, don't get confused by it. Try to always understand the meaning behind it. That's why we had so many lectures on the attention mechanism before, just so that when we reach this stage, understanding all of this becomes easy. So remember, until this stage, we have computed the attention score. So this is exactly what is done here. Remember what we saw on the whiteboard. To compute the attention scores, we'll take the queries and we'll multiply with the keys dot transpose 2 comma 3, because in transposing 2 comma 3 we'll make sure that the correct queries and the attention and the keys transpose product is taken to calculate the attention scores. And this is also implemented in the code. So if you see in the code, the attention score is the product, is the scaled product between queries and the keys. Great. So here it's shown dot product for each head. Now you'll understand why I'm saying each head, because as I showed you before, each head has number of tokens, comma number of tokens attention scores. And for one head it's here, and for the second head it's below. Okay, now we come to the next step. The next step is to essentially find the attention weights. Okay. So, and if you look at this attention score over here right now, you'll see that for every token, there is an attention score with respect to every other token, right? But that's not what's the mechanism in causal attention. What causal attention says is that when you look at the, you should only look at the attention score between the and what comes before it. So the and the, all the other elements here. So let me show them with a different. Let me first rub this so that, yeah. So what causal attention mechanism dictates is that when you look at the first word, which is the, only the attention score between the and what comes before it should survive. So all of this should go to zero. If you look at cat, only the attention score of the words which come before, so the and cat should survive. This should go to zero. And when you look at sleeps, attention scores of all will survive because all the words come before it. This is what we are actually going to implement next. So to do that, first what we are going to do is we are going to take the attention scores which we have and replace all of the elements above the diagonal with negative infinity. The reason we replace this with negative infinity is because after this point we are going to implement the softmax function, so that each row sums up to 1. And when we implement softmax, whatever is there in the infinity will automatically go to 0. So it will kill two birds in the same stone. We will implement the causal attention mechanism, and we'll also make sure that all the rows sum up to 1. But before we implement softmax, we do one more thing. We divide every single element here with the square root of the head dimension. And this, when we looked at the lecture for self attention, we saw why this is done. This is essentially to make sure that the variance between the, when we take the dot product between the queries and the keys, the variance scales up with the number of dimensions. And to prevent the variance from blowing up, we have to divide by the square root of the head dimension. This also makes sure that the values in the values before we compute the softmax are not very high, and that's generally useful for back propagation and leads to stable gradients. So what we'll be doing is that the head dimension, as we saw, is 3, right? Because the d out is equal to 6 and the number of heads is equal to 2. So each head dimension is equal to 3. So we will divide this after replacing the elements above the diagonal with negative infinity. We'll divide this with square root of 3, which is square root of head dimension. And that leads to this matrix over here, or this tensor, I should say. And then we apply softmax to this tensor. So we make sure that every row here sums up to essentially, so if you look at each row in this, you will see that it's summing up to 1. And the reason it sums up to 1 is we are applying softmax. So now I can make claims, interpretable claims. So when I say that when I look at the second token cat, I should pay 96% attention to the, and I should pay 4% attention to cat. When I look at sleeps, I should pay 4% attention to the, I should pay 26% attention to cat, and I should pay 69% attention to sleeps. Remember, these values are not optimized, but when they are optimized, when we look at back propagation later, uh, the fact that these values sum up to 1 will carry meaning, because we can make interpretable statements such as what I was making right now. Remember that after we are going to apply softmax, the attention weights have exactly the same dimensions as the attention scores, which is going to be the batch size, number of heads, number of tokens, and number of tokens. So this is the dimension of the attention weights, which is 1 comma 2 comma 3 comma 3. So if you look closely, to go from attention scores to attention weights, we actually have a rich number of steps, and it's important for you to understand all of these. First, what we did is we applied a mask so that all elements above the diagonal are negative infinity. Then we divided by the square root of the head dimension. Then we applied softmax. This is how we got the attention weights. Now let's see how that is done in the code. Before that, one thing, usually we can also implement dropout after this. So you can mention a dropout rate, which is actually one of the arguments in the multi-head attention class. But here I am not implementing dropout for the sake of simplicity. So if you look at the code here, we have got the attention scores. The first step, as I said, is to create this mask and then apply this mask to the attention scores so that all the elements above the diagonal are negative infinity. That's what this step is doing. Here the mask actually has also been defined over here. See, this is the upper triangular mask, which is all the elements above the diagonal are 1. Then they are replaced with negative infinity, and that's applied to the attention scores. So this will ensure that all the elements above the diagonal of the attention scores are equal to negative infinity. And we are only considering context length here. Why context length? Because let's say context length is 3. It means that maximum if 3 words are given, we can make prediction of the next word. So when we implement this dropout mask, we only implement a mask of context length, comma context length. There is no point in implementing a bigger mask because anyway we are not going to look at more tokens than the context length at a time. And if it happens that we are looking at a batch where the number of tokens are less than the context size, this statement makes sure that then the mask stops at number of tokens. But this is a detail which probably you can overlook right now. If you are understanding all the other things, that's what's the most important. If you understand this minor detail, it's awesome. Then the next step is to apply softmax. But as I told you, before applying softmax, we divide every element with the square root of the head dimension. If you look at the keys dot shape, let's look at keys dot shape. This is going to be the keys dot shape. So keys dot shape of -1, which means that we are going to look at the last dimension, which is the head dimension. So we are essentially dividing by square root of head dimension here, and then we apply the soft max. Why dimension equal to -1? Because we need to make sure that all the columns of a row sum up to 1. And then, as I said, we can even implement dropout if needed towards the end. So up till now, we have reached a stage where we have obtained the attention weights basically, and I hope you understand the meaning behind this final attention weight matrix. It's not just important to understand how the dimensions work. So to make sure you understand the meaning, let me go through the meaning of this attention weight matrix once more. Um, this what I'm highlighting right now is the attention weights for the first head. This second block is the attention weights for the second head. In each attention head block, you will see that the size is number of tokens rows and the number of tokens columns. So each value is essentially the attention weight between, let's say, this is the attention weight between the second row, which is the second token, and the second token. This is the attention weight between the third token as the query and the first token as the key. So basically you will see that every single element here has some meaning. It essentially encodes the attention weight between the query and the particular key. Okay, now let's go ahead. The last step which we are going to implement is that we have to calculate the context vector. Remember, the aim of all the attention mechanisms is to ultimately compute the context vector matrix, and this is exactly what we are going to do. And to compute the context vector matrix, we take the attention weights and we multiply them with values. Remember, the value matrix was the matrix which we had computed earlier. Let me show you where the value matrix was in case you have forgotten it, because we have done so many things. Yeah, so here was the value matrix which we had computed. We have not used it until now. It will only be used in this last step. Okay, so the attention weights will be multiplied by the values matrix to get the context vector matrix. So let's see how the dimensions work out here. Okay, The attention weights, as we looked earlier over here, the attention weights have the dimensions of b, comma number of heads, comma number of tokens, comma number of tokens. And as we saw earlier, the values matrix has the dimensions b, comma number of heads, comma number of tokens and head dimension. So effectively, let's see whether these matrices can be multiplied. So this is number of tokens and number of tokens, and that will be multiplied by number of tokens and head dim. So the number of columns here is number of tokens, and the number of rows here is number of tokens. So the number of columns in the first matrix are matching the number of rows in the values matrix. So we can see that these two matrices can essentially be multiplied. So multiplication is possible, and now let us see how the multiplication will actually work in practice. This is the final attention weights matrix. Here it's mentioned attention scores, but I should have called it attention weights. Remember, there is a difference between scores and weights. Attention weights, in the attention weights, each row sums up to 1. That's not the case with attention scores. Okay. So this is the attention weights, and this is my values, this is my values matrix. So this 1 comma 2 comma 3 comma 3, and this 1 comma 2 comma 3 comma 3, and when we multiply, the resultant output will be b, comma number of heads, comma number of tokens, uh, comma the head dimension. So here you can see that the context vector output is b, comma number of heads, comma number of tokens, comma head dimension, which is 1 comma 2 comma 3 comma 3. Let's interpret this again. So here you can see that there are two heads. So this is head number 1 and this is head number 2, and in each head there are number of tokens. So if you look at each head, there are 3 rows. So each row corresponds to one token. But now if you look at what each row represents the context vector for that particular token, and it has the dimensions equal to head dim, because head dim is equal to 3. So that's the meaning of this context vector matrix which we have reached. But now remember, there is a problem here, right? Or not a problem, but we have to somehow merge this number of heads and head dimension back together, because the resultant context vector matrix, remember what we saw earlier, the, let me scroll up a bit. So if you looked at the goal which we had when we started this lecture, the goal was that the resultant context vector matrix should have the dimensions of, uh, yeah, as I mentioned to you, the goal was that the resultant context vector matrix should have d out, right, as the dimension. So we should again pull back the head dimension and the number of heads together, so that we can get the resultant matrix which has the d out dimension preserved. Whereas let's see what we have obtained until now. Well, until now, the context vector matrix which we have obtained, yeah, the context vector matrix which we have obtained has number of heads and head dimensions in separate positions. So first what we'll do is that we'll bring them closer together so that we can then merge them to get the D out. So what we are going to do is, now we are going to swap this number of tokens index with the number of heads index, so that the dimension of the context vector matrix is, so that the shape of the context vector matrix is changed. So the next step is basically step number 10, and that is to reformat the context vectors. So currently the context vector shape is b, comma number of heads, comma number of tokens, comma head dimension, right? And I want the number of heads to come here so that they are closer to the head dim, and I want the number of tokens to go here. So I want the resultant matrix to be b, comma number of tokens, comma number of heads, comma head dimension. So essentially what I will do is, after I compute the context vector matrix, I'll do a transpose of the first index and the second index. And so the resulting context vector matrix now, which has the dimensions of b, comma number of tokens, comma number of heads, comma head dimension, looks like this. So here you see now the interpretation is different. Now this is my first token. Now the grouping is with respect to tokens. This is my second token and this is my third token. and in each token there are two heads. So if you look at the first token, there are two heads, and if you look at the first head, this is the vector with respect to the first head, the context vector, and the second row is the context vector with respect to the second head for the first token. Now let's see how all of this is implemented in code. Actually, all of what we saw right now is just implemented in one line of code. But to understand this, we really had to understand first of all how the attention weights are multiplied with values. The multiplication really makes sense. And why do we do this transpose 1 comma 2? The reason we do this transpose 1 comma 2 is to get the context vector matrix in this shape. The reason we get it in this shape is now you can see the number of heads and head dimension are closer together, so we can merge them into the d out more easily. So here you can see this is what we have reached up until now, where the context vector is obtained and it's in the correct format. Now the last step what we have to do is that we have to let me show you. The last step what we have to do is essentially we have to combine the results from multiple heads. So see, this is the context vector matrix which we have obtained right now, right? So if you look at the first token which I have highlighted over here, this is the first head and this is the second head. Now what I will do is that when I look at the first token, I will combine these two together into one row, so that it will be 6. The dimension will be 6. So so here these are 3 and these are 3, right? So I'll combine the outputs from both of these heads into one output. So let's see how this looks like. So then the first row will, so then we'll flatten, this is called flattening, we'll flatten each token output into each row. So the head 1 and head 2 outputs are combined together. So if you look at the final output, the first row consists of merging of the two heads for the first token. The second row consists of the merging of the two heads for the second token. So for the second row, we merge these two outputs into one single row. And for the third token, we merge these two outputs into a single row. So you'll see that this is the third row. So this now what I'm showing on the screen here is my final context vector matrix. And how to interpret this? If you look at the first row is the context vector for the first token. First row is the context vector for the first token. Why does it have 6 elements? Because d out is equal to 6. The second row is the context vector for the second token, and the third row is the context vector for the third token. So overall, you see, we first split the d out into number of heads and head dimension, and now we brought it back together to get the d out. So in the final shape, you will not see the number of heads. It's all merged into this d out. So this is my final answer right now, and the shape of this is 1 comma 3 comma 6, which is b comma number of tokens comma d out. So this is exactly what is done here. What we do is that we take this context vector and we reshape it into b comma tokens comma d out. Why this contiguous is needed is because we want to make sure that when we reshape matrices, they are in the same blocks of memory. So when we reshape tensors, let's say, and if they're in different memory blocks, it becomes difficult. So first we make sure that using this contiguous, they are in the same memory block. Then we reshape them so that the final output is b, which is the batch size number of tokens, which is equal to 3 in the example we saw, and d out, which is the output dimension, which is equal to 6. And then there is an optional projection layer towards the end. So if you look at the output projection, it's again a linear layer and whose parameters can be learnt. This is not really necessary, but sometimes it is implemented in practice. Now, this is exactly the entire procedure for how the multi-head attention is implemented from scratch. And here we saw the multi-head attention for the example which we have. So the first token is again the 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 second token is cat, and the third token is sleeps. Let me write this again. Yeah, the third token is sleeps. So you see, through this entire procedure, we obtained the enriched context vector representations for these tokens. Similarly, when you deal with large volumes of text, you take sentences, you break them down into tokens, then into token IDs, then into input embeddings, and similar to this procedure, you get context vectors for each token which you have. Ideally, when we run the actual code, we'll have multiple batches, but I showed only one batch right now for simplicity. So to whoever who have reached until this stage, I want to say that thank you for following with me for so many lectures. I know these lectures are becoming very long, but unless I explain every single thing in detail, it's very difficult for you to understand all the details. So congratulations, if you have reached this lecture, you have successfully understood how the multi-head attention works. And I think there are very few people who really understand this entire piece of code block by block. Okay, so I'll share this notebook with you, and whatever I explained to you on the whiteboard, all the steps which I laid out in front of you on the whiteboard, all of those have been explained here as step 1 to step 11. And I have explained, added a detailed explanation of the multi head attention class. In today's lecture, I did not just want to read this, but I wanted to construct a practical example to show you how the dimensions actually work. And it took me a long time to make this example, but now I think it's worth it because it really helped me explain it, and I hope you understood it better. So now we can actually test out the multi-head attention class. So here are my inputs. As I showed you on the whiteboard, we have three tokens and we have six. The embedding dimension is six. The only change here, what I'm going to do, I'm going to create a batch. So I'm going to create a batch of two such inputs, and I'm going to stack this batch on top of each other. So I'm going to assume a d out equal to 6, exactly what we saw on the whiteboard, and context length equal to 6. And then we are going to implement the multi-head attention class. So d in is equal to 6, d out is equal, so d in is equal to 6, right? Because each token has the input embedding dimension of 6. D out equal to 6. The context length which we are using is equal to 6. Then yeah, the dropout rate which we are considering is 0. We can even include the dropout rate. So the dropout rate will change this last layer of dropout and randomly block out some attention weights. This is good for generalization. And the number of heads equal to 2. So we create an instance of this class and then create the context vector matrix. And you will see for the first batch, the context vector matrix has 3 rows and 6 columns. Let's see if the shape matches what we had seen on the whiteboard. uh, okay, so let me scroll down below. Yeah, this is the final context vector matrix which we had obtained. Yeah, so this also had 3 rows. Okay, I think I need to scroll up a bit. Yeah, this is the final context vector matrix which we obtained, and this also had 3 rows and 6 columns. The values might be different because we have done the initializations differently. Here I have taken random initializations. In the Python code, there are some other initializations. Every time you initialize, we take from a Gaussian distribution. So the values might be different, but let's check the shape. So this is 3 comma 6, 3 rows and 6 columns. And here also we can see that 3 rows and 6 columns. Awesome. So the shape matches, but you will see that since there are two batches, here is the context vector matrix for the first batch and here is the context vector matrix for the second batch. So the multi-head attention class which we defined is extremely powerful because it can also handle multiple batches at once. We can even do 50 data batches, and then it will just have one, two, it will have 50 such context vector matrices. Okay, that's it. That brings me to the end of this section or the end of this lecture. So, in this lecture, we implemented the multi head attention class that we'll be using in the upcoming lectures to implement and train the LLM. This code is fully functional, but we used relatively small embedding sizes and number of attention heads to keep the outputs readable. So, as I showed you, we only use two attention heads, but GPT-3 actually used 96 attention heads. So the smallest GPT-2 model had 12 attention heads and a context vector embedding size of 768. The largest GPT-2 model had 25 attention heads and a context vector embedding size of 1600. And GPT-3 has even higher. So the GPT-3 largest model has 96 attention heads, I think. And generally in GPT models, the D in is equal to D out. In the example which we saw, D in was equal to D out equal to 6. But here the D in and D out are much larger, around 768, etc. Again, thank you so much everyone for reaching the end of this attention series. It's been one of the longest and most comprehensive series which I have covered, and I really enjoyed learning about all of these things. I can see that many LLM practitioners cannot understand these dimensions, or they do not take time to go through understanding the theory, the building blocks behind how the attention mechanism works. They just implement the code bases which are available, which completely abstract away all of these things. So I don't think that's the good way or the correct way to learn about large language models. If you want to be a true LLM engineer or a machine learning engineer, you have to understand how nuts and bolts work. Otherwise, you might be able to deploy applications, but to make real inventions, you will have to go into the code base, change a few things, understand dimensions. As you might have seen, and I have stressed this many times, dimensions and linear algebra are at the heart of becoming a very strong ML engineer. It all comes down to dimensions. Other students might be scared of a four-dimensional tensor, right? But if you understand how it works based on what I showed to you on the whiteboard, my aim is that you should not be scared of these higher dimensional matrices. Once you write it down, and once you understand what's going on, it really becomes easy. That's why I really recommend writing things down. You can write on a whiteboard, you can even write on a piece of paper, but make sure you write things down. Then you will remember them for a longer period of time. I hope you all are enjoying these lectures. Thank you so much, everyone, and look forward to seeing you in the next lecture, where we'll actually start building the LLM model. Thanks a lot.